Good morning, this is Dr. Jingbo Louise Liu from Texas A&M University, Kingsville. Today we are going to discuss your last experiment, number 10, galvanic cells and the Nernst equation. You have 4 different objectives. First one, to determine the relative reduction potential for a number of redox couples, to develop the understanding of the movement of electrons, anions, cations in your galvanic cell, to study factors affect on your cell potential, to estimate the concentration of your ions in your solution by using the Nernst equation. The key points in your redox reaction. Number 1, oxidation reaction, meaning electron loss, always accompanied by the reduction reaction, meaning electron gain. The oxidation reaction, lots of time we call the LEO. Electron loss called the oxidation reaction, LEO. Oxidizing agent by itself is reduced. Reducing agent by itself is oxidized. The number of electrons totally gained by oxidizing agent and the one lost by a reducing agent, they are always the same. If you lose 2 electrons, gain 3 electrons, you totally involved in 6 electrons transfer, 2 times 3. The galvanic cell, lots of time people also consider it voltaic cell, meaning the cell is spontaneous reaction involved in. For example, I have this voltaic cell composed of the zinc nitrate solution or zinc chloride solution. So you place a zinc electrode, another one is copper sulfate, a copper nitrate solution. You use a copper electrolyte. You hooked up this zinc and copper, and you place a salt bridge in the middle, so you are going to form an electrical circuit. So what you are going to find, you find 3 different key components. The first one on your right hand side, this is your cathode. On the left hand side, this is your anode. In between, you must have a salt bridge to connect 2 half cells together. In your cathode, usually you have the positive sign. If you have your little battery, you have the positive sign, that's your cathode. Cathode is subject to the reduction half reaction. For example, your copper 2 plus aqueous will gain 2 electrons to produce copper metal. What you are going to see, you see your copper solution, blue color faded, and less becomes colorless. And you're also going to see lots of little tiny particles deposit on your copper electrode. So that's what your observation. Copper nanoparticles actually is going to be formed. Your solution blue is going to fade away sooner or later. This reaction called reduction reaction. Reduction reaction occurs on your cathode. Lots of time we are going to say red cat. On your anode side, usually your anode has a negative sign. The oxidation half reaction occurs at your anode. For example, you have zinc 2 plus zinc. That's your redox couple. So what's going to happen? Your zinc metal is going to be oxidized to zinc 2 plus aqueous and produce 2 electrons. Again, this anode is related to the oxidation reaction. What you are going to see, you are going to see your color has no change. However, your zinc electrode is going to be slowly dissolved into the solution. So this diagram showed you the chemical reactions for the cathode, chemical reactions for the anode. You're adding these 2 reactions together, you are going to gain your overall reaction for this galvanic cell. Followed by, we want to know what's the notation for the voltaic cell. So voltaic cell is one type of the galvanic cell. So you again cathode Cathode you use positive, anode you use negative. Cathode is reduction, anode is oxidation. What's the function of your salt bridge? Your salt bridge is acting as an internal circuit. So you have three different functions. Number one, the salt bridge helps to complete the construction of your galvanic cell. Salt bridge allows the ion movement from one side to the electrode, from one side of the electrode to another side. And then the salt bridge also maintains the charge balance and the electrical neurality. So when we see this, this is your balanced, circuited, completed circuit galvanic cell. Your electron flow normally is from your A anode to your C cathode. Your ion flow, usually positively charged ion, diffuses from your electrolyte in your anode to the cathode. Electron goes through from anode to cathode through external wire. Positively charged ions such as sodium, such as proton, going to be diffusing through the electrolyte in anode to the electrolyte in cathode. So your salt bridge, the salt bridge can be prepared simply using a filter paper to the sodium chloride aqueous solution. That's how you determine it. So related to the galvanic cell notation, usually you are going to place cathode on the right hand side, anode in the left hand side. You use a double straight line to represent the phase boundary between two different half cells. In the same cell, you also have two different phases. One phase is called the higher oxidation state. Another phase is called the lower oxidation states. In this case, you use a single line to separate two different phases. The same way for your anode side, you have your lower first, higher, higher, lower, higher to lower reduction, lower to higher oxidation reaction. The examples will be your put a double straight line, so you have your copper 2 plus aqueous single straight line and copper solid. This is your cathode compartment. So on the anode compartment, place your higher oxidation number species closer to your double straight line, and then using a single straight line to separate your solid and aqueous solution. In your anode, you have your zinc is going to be oxidized to zinc 2 plus and again produce 2 electrons. Cathode is your reduction reaction. Copper 2 plus is going to gain 2 electrons to produce your copper metal. These reactions, you are going to use copper and zinc metal by themselves as electrode. They call the active electrode. Sometimes you have solutions. You need another electrode such as graphite. They act as inert electrode. So also double straight line represent the phase boundary between two different half cells. In the same cell, you have different chemicals, different phases, you using single line. If you have two different aqueous solution, not solid or liquid, lots of time we're using camera to separate it. So this is about the notation of galvanic cell. So how you are going to determine the cell potential? First of all, if you have everything operating at the standard state, the standard cell potential equals to the cathode reduction potential minus anode standard reduction potential. So you can calculate the unknown E cell with the standard reference of hydrogen electrode. It's called standard reference electrode. SRE also is a hydrogen electrode. So this diagram again showed you about the standard hydrogen electrode reference. You consider that reduction potential is 0. Proton to hydrogen, proton to hydrogen, you consider is 0. reduction potential is 0, I mean. And then you also want to understand what's the concentration impact on the cell potential. You are going to use the Nernst equation. We already know delta G equals delta G naught plus RT ln Q. And then you can correlate delta G with the cell potential. Delta G equals negative NF E cell. So delta G naught equals negative NF cell potential at the standard state plus RT ln Q. This Q you call the chemical quotient. Also you use the mass action law to determine it. And then this Q is a product of your molar concentration of your product divided by the product of molar concentration of your reactant. So I simplified into cell potential equals to the E0 cell potential minus 0.592 divided by N times log log Q. If it's equilibrium, this cell potential will be 0. So this N represents the total number of electrons transferred. Q again is called the chemical quotient. E cell is the cell potential which you measured. E cell 0 E naught. This E naught is the standard cell potential which you can calculate it. Another point of a galvanic cell is related to the concentration. Therefore, people call the concentration cells. You have the same chemical species. One is a copper nitrate that have higher concentration. Another one you have lower concentration. In this case, the chemical reaction, electrochemical reaction will occur unless two sides concentration will be equivalent to each other. In this case, you just have a higher concentration becomes a lower concentration of your cations. This is about the concentration cell. And then related to the spontaneity of your redox couple, so we have several points. Number one, by convention, your electrode potential written down as reduction. You find the number, those numbers, reduction potential, reduction couple. So you usually put up Ag plus, this higher oxidation number and lower oxidation number. Bismuth, Bi3 plus, Bi metal. So this number is a reduction potential. And then one pyrene, two half cells. You have one half cell, another half cell. You compare them. So you are going to reverse one of the half cell which is in the anode side. So reduction half cell potential and oxidation half cell potential, so you can add them together. I personally, I don't like this reverse. I simply use E cell equals E cathode minus E anode. For example, I have bismuth. This bismuth 3 plus bismuth, this redox couple has a reduction potential 0.20 voltage. Your silver plus silver redox couple has a 0.80 voltage. The cell potential, if you pair these two half cells together, the cell potential equals cathode equals bigger value minus the smaller value, 0.80 minus 0.2, 0.6. So meaning this silver plus silver will be your cathode. Your bismuth 3 plus and bismuth will acting as your anode. Anode meaning this bismuth is going to be oxidized. Your Ag plus will be reduced. So that's how you write down the balanced reaction. And then about Nernst equation, we already essentially gave you the Nernst equation. So you need to know how many electrons transferred. From silver plus to silver is 1 electron. From bismuth to bismuth 3 plus 3 electrons. Totally have 3 electrons, meaning this N will be 3. If we gave you the different concentrations of bismuth and the silver, so you simply replace the concentration into your Q. So you can determine either the concentration of bismuth or determine the cell potential. So that's what we are going to ask our student to work on it in the lab. So again, based on this bismuth and the silver cloud and the silver electrode, if you change the concentration, so make sure you use this Nernst equation. So I give you another one. If you have sour chloride, it becomes sour and sour plus and sour chloride. This reaction has a reduction potential 0.23 voltage. And on the other hand, you have another one which is a little bit more active ion. Fe2 plus gain electrons becomes Fe. This redox couple has a reduction potential negative 0.44. Which one will be your cathode? The bigger one will be a cathode. The smaller one will be your anode. Therefore, you can calculate the delta E cell standard. And then this E cell standard equals cathode minus anode. In our case, 0.23 minus negative 0.44. So you calculated the standard cell potential. And then you simply replace your numbers into this Nernst equation. If you already know this chloride concentration, you want to calculate Fe ion 2 plus concentration, use the Nernst equation to do the calculation. So that's what I showed you my results. And then about the half reaction method for balancing your reaction is very commonly used, because you have two different half reactions. You balance the first one, you balance another one, and then make sure you have the total number of electrons transferred must be the same. I think up to this point, I will call it a day today. Thank you so much for listening. Stay safe and stay healthy.